All right, everyone. Welcome to our final talk of the week of the conference. I'm almost sad to see it finish, but I think it's been a great event. I'm glad that everybody's attended so well and from all the beautiful talks that we've heard. And as I said, we're very lucky. We're ending on a high here with Georgios Moschidis, who's going to give us a beautiful talk on his incredible work on weak turbulence for the Einstein-scalar field system. Georgios, please.
Well, Martin, thank you very much for the wonderful introduction. And of course, thanks for the invitation. And as the title suggests, today we'll actually mostly speak about the instability of ADS, which is an example of weak turbulence appearing in for the Einstein field equations. But also I want to speak a little bit about some related problems. So let's see how much I'll be able to say. So give me a second. Yeah, not work, just, yeah. Okay, so in this talk, we'll be mainly interested in the case of the Einstein vacuum, of the Einstein equations, let's say more general, with a negative cosmological constant. And in this case, we'll be interested in the most trivial solution of those equations, which is under de Sitter spacetime, which most of you are familiar, of course, with this spacetime. I've just written down the metric explicitly here in time polar coordinates. And this metric, for those of you who are not very familiar with that, you should think of it as really as a generalization of hyperbolic space to the Lorentzian setting. In particular, an interesting feature of this spacetime that we'll make use of is the fact that it can be conformally identified with the interior of a cylinder. In particular, if we use as conformal factor this coefficient of dt squared here, and we multiply the whole metric with the inverse of that coefficient, then the metric that we end up with is that of the product metric on R times the northern hemisphere of S3, rescaled by a factor depending on the precise value of lambda here. And this is really a conformal transformation, and therefore this transformation preserves the causal structure of the spacetime. And through this transformation, it's easy to see that ADS spacetime has the causal structure of the interior of a cylinder, and in particular, it's not globally hyperbolic. What do I mean by that? What I mean by that is that the spacetime, of course, has a time-like boundary at infinity, corresponding to R equals infinity. This is the conformal boundary, if you want, of this cylinder that I've drawn here. And due to the presence of that boundary, we're not, if we want to study hyperbolic equations such a background, let's say, for example, suppose that we want to study the scalar wave equation on ADS spacetime, we cannot uniquely determine a solution just by prescribing initial data, say at t equals 0. We also have to prescribe boundary conditions on this boundary at infinity. For example, Dirichlet or Neumann boundary conditions, more than that in a minute. And what does the motivation to study ADS spacetime, or more generally asymptotically ADS spacetimes, come from? Well, it comes surprisingly from the high energy physics community, where those spacetimes appear very prominently in the context of the holographic principle, more particularly the ADS CFT conjecture. However, in this talk, I'm not going to talk about any of that, any of the high energy physics stuff. Instead, we're going to use the boundary of ADS, or more generally of asymptotically ADS spacetimes, as a model for confinement for the Einstein equations. So what do I mean by that? Well, first of all, let's look at the framework that we're going to employ. We want to study in this talk asymptotically ADS solutions of the Einstein equations. Now, the Einstein equations are of hyperbolic nature. And exactly because we have this boundary at infinity, the right setting to study those solutions is through the initial boundary value problem. Right? And how do we formulate the initial boundary value problem? Well, we have to prescribe first initial data along a space like hypersurface, a surface like t equals 0 on ADS. And those initial data have to satisfy the constraint equations, which I've written down here in the vacuum case. And for the next few slides, I'm just ignoring the presence of matter. I'm just looking at the vacuum Einstein equations. And moreover, we also have to prescribe boundary conditions at the boundary at infinity. And since this is a conformal boundary, these boundary conditions have to be prescribed in terms of the conformal geometry of that boundary at infinity. And of course, if we prescribe initial data here on this space like hypersurface and boundary data here on the boundary at infinity, we have to make sure that some compatibility conditions are satisfied at the corner here of intersection, in order to be able to get, let's say, a smooth solution of this initial boundary value problem. Okay, so this is, morally speaking, how the initial boundary value problem is formulated. But of course, the natural question is does this formulation give rise to a well-posed initial boundary value formulation? And that's a very non-trivial question to ask, among other things, it's complicated exactly because this boundary is a conformal boundary at infinity. It's not a regular boundary. And the first person who addressed the issue of well-posedness was Helmut Friedrich, who in 1995 proved the following theorem. He actually discovered the following class of boundary conditions that lead to a well-posed initial boundary value problem, which is the following. He said that for any smooth prescription of the conformal geometry of this boundary at infinity, and any choice of asymptotically ADS initial data, which are asymptotically smooth and asymptotically ADS, then there exists a smooth solution to the vacuum Einstein equations, at least locally in time, attaining those initial and boundary data. And moreover, this solution is geometrically unique. Now, the class of boundary data constructed by Helmut Friedrich is very large, as you see. However, within this class, there is a unique boundary condition that is reflected, namely a unique boundary condition for which a proper energy flux at infinity vanishes. And this boundary condition is the one that stipulates that the conformal geometry of the boundary is that of the round cylinder, namely that of the boundary of anti-de Sitter spacetime. And you can really think of this boundary condition as the analog of Dirichlet-Neumann boundary conditions in the case of the linear scalar wave equation. Now, let me focus a little bit on the issue of geometric uniqueness here. And first of all, let's note that, okay, here we're talking about the asymptotically ADS initial boundary value problem. But of course, one could also be interested in the initial boundary value problem, more than, let's say, even in the case where the boundary is finite, it does not lie at infinity. And in fact, geometric uniqueness in the case of the regular initial boundary value problem, where the boundary lies at a finite distance, is actually trickier. And it was only, geometric uniqueness was actually only recently proven by Fournodoros and Skulevisi for a large class of boundary conditions, which includes the case when the boundary is totally geodesic. This class is the class of umbilic boundaries. But okay, let's go back to the asymptotically ADS setting. And I told you before that we're going to use the boundary at infinity as a source of confinement for the Einstein equations. And the way we're going to do that is that we're going to assume for the rest of the talk that whenever we talk about boundary conditions, we'll assume reflecting boundary conditions at infinity. And those reflecting boundary conditions will have the effect of trapping, if you want, the energy of our solution inside the spacetime and not allowing it to escape through the boundary. Okay, what do I mean by that? This is not a very well formulated sentence. So what we're going to study is the following dynamical question. So now that we have the well-posedness of the initial boundary value problem at hand, we can ask the question of what happens to specific sets of initial data if we let them evolve for a long period of time under suitable boundary conditions at infinity. And the simplest question we can ask in this setting is that of the stability properties of the trivial solution under reflecting boundary conditions. Right? So in particular, what happens to ADS if we perturb its initial data a little bit and let them evolve in time through reflecting boundary conditions at infinity. And it's easy for you to realize that, in fact, one should not expect ADS spacetime to be stable in this setting. And why is this the case? Well, let's look at the simplest toy model for the Einstein vacuum equations, namely the linear scalar wave equation. Let's assume that we're looking at the linear scalar wave equation on ADS with Dirichlet conditions at infinity. Then we know that as the scalar waves evolve, their energy is conserved. This is exactly because we imposed reflecting conditions at infinity. And in particular, this means that their energy cannot decay as time goes to infinity. But now, exactly because we're looking at a spacetime for which the time slices are conformally bounded, the fact that the energy does not decay means that the pointwise norm of the scalar field also does not decay. And this means that once we look to a more complicated equation, once we turn on some nonlinear interactions, then this non-decaying property of the linear scalar fields mean that actually the nonlinear solution might be able to self-interact over long periods of time and produce non-trivial effects. In particular, something like that already happens in the equations of fluids, where one sees a phenomenon of turbulence appearing. So the natural question to ask is the following. In this setting of confinement for the Einstein equations, so when we look at the perturbations of ADS, can you see weak turbulence appearing for the Einstein field equations? And back in 2006, Decoherence and Holzigel conjectured that yes. In fact, the conjecture that they proposed was the following, that there exist arbitrarily small perturbations of the ADS initial data for the vacuum Einstein equations, such that if we let those data evolve with reflecting boundary conditions at infinity, and we wait for sufficiently long time, then we will eventually see a black hole region appear. And of course, so what do I mean by black hole region here? A black hole region here is simply a region of the spacetime that cannot be seen by conformal infinity, in analogy to the asymptotically flat case. And of course, since ADS spacetime does not contain a black hole region, this is a geometric statement of instability. And let me, again, why did I say that this is related to the phenomenon of turbulence? This is because, morally speaking, we expect a black hole to be formed when energy is concentrated at small enough scales. And again, we already had a little bit about it before in the question, but you can think of this statement as somehow analogous to the Hooke conjecture, put forward by Kip Thorne in the early 70s. And the Hooke conjecture says that a two-dimensional surface in the spacetime is trapped if it's the energy contained in that surface, appropriately defined, let's say the quasi-local energy, divided by the diameter of that surface, also appropriately defined, let's say the intrinsic diameter of that surface, is bounded from below by some explicit constant, of course, depending on all those choices that were made in the definition of the left-hand side here. So in other words, a two-dimensional surface is trapped and therefore is contained in a black hole only if its energy, the energy contained there over the diameter is not too small. And since we look at initial perturbations which are initially small and therefore have small energy, in order to see a black hole forming, we expect that this energy is going to be concentrated at very small scales. Okay, let me make a few more remarks here. So first of all, what do we mean by smallness of the perturbation? Well, it's not clear in the statement of the conjecture as I wrote it down. And there are two choices one can make. So one can be quite maximalistic with their requirements and ask for initial perturbations which are small with respect to a very high regularity weighted Sobolev norm. These are, for example, the spaces in which Helmut Friedrich proved local well posedness for the initial boundary value problem. Or one could be a bit minimalistic in the requirements and just ask for smallness with respect to a norm in which, first of all, the initial boundary value problem is well posed. You have existence, uniqueness, and cosystability, and for which, moreover, let's say we have a statement like that for a norm like that, let's say Minkowski spacetime is stable, like a norm in which, in the absence of confinement, we wouldn't have any problems with stability. And let me already stress here that using the total ADM mass at infinity to measure the size of the solutions is not a good enough choice of norm. This is a very low regularity norm, and in fact, the equations are super critical with respect to that norm. And therefore, this means that one can find initial data which are small, which have small ADM mass, but which nevertheless create a black hole in arbitrarily small times. Right? So that's not a good choice. I'm just mentioning this because in the physics literature, it is this quantity is often used as a norm of the initial data. Now, let me also stress that it's crucial for the validity of this conjecture that the boundary conditions chosen at infinity are reflected and therefore introduce confinement. If one switches instead attention to, let's say, dissipative boundary conditions, and more precisely to maximal dissipative boundary conditions, then a result by Holzinger, Luxem, Levy, and Warnick says that linearized perturbations of ADS spacetime actually decay very fast. They decay at a super polynomial decay rate. And such a result one would expect to be generalizable to the nonlinear case. And somehow this should be seen as, compare this to the statement that I wrote down before for reflecting boundary conditions. And finally, let me stress that despite the fact that I wrote down the conjecture here for the vacuum case, the conjecture is also valid for any matter model that is reasonable, in the sense that any matter model that in the absence of confinement does not cause us any trouble. Like, for example, any matter model for which Minkowski spacetime is stable under small perturbations. Of course, the statement about the vacuum case is the cleanest one. But as we will see right now, it's actually easier to go through matter in order to understand this conjecture better. Okay, so that's the statement of the conjecture. And how can one attempt to establish the ADS stability conjecture? Well, in order to prove the conjecture, one has just to exhibit a family of initial data which eventually collapse into a black hole, which can become arbitrarily small initially, but eventually collapse into a black hole. And in order to do that, the easiest thing to do is to actually find some reduction of the system, some symmetry class, in which the Einstein equations reduce to a 1+1 dimensional system from a 3+1 dimension. Now, in 3+1 dimensions, of course, the only surface symmetry that would have this property would be spherical symmetry. But unfortunately, in the vacuum case, we cannot study the evolution of initial data under spherical symmetry because within spherical symmetry, there is only one solution to the Einstein equations which has non-trivial center, that's ADS spacetime. So there are no dynamics in spherical symmetry. And that's why people studying these problems of R have instead looked at the case of the Einstein-scalar field system within spherical symmetry, because that's a system which is 1 + 1 dimensional, but nevertheless preserves many of the qualitative characteristics of the vacuum Einstein equation 3 + 1 dimensions. So in particular, what we're going to do is that we're going to, so the equation for the scalar field for us is going to be a Klein-Gordon equation, where I'm going to use this parameter alpha here for the Klein-Gordon mass. So whenever you see an alpha from now on in the next few slides, this is going to refer to the Klein-Gordon mass of the scalar field. Okay, so let's go back to a little bit to the formulation of the initial boundary value problem, because now we have to be a little bit more specific about how we prescribe boundary conditions. And since we're going to study the problem in spherical symmetry, we know that most of the most important parts of the dynamics are going to be captured by the scalar field part, because the geometry, if you want, so once, let's say, the scalar field is determined, the geometry of the space-time is going to be determined through the scalar field by, let's say, the constraint equations along its slice. Okay, so let's see how we prescribe boundary data for the scalar field. And in order to understand that, let's first look at the trivial case of a free scalar field on ADS spacetime. Now, if we have such a free scalar field on ADS, we can formally expand phi into, let's say, an asymptotic series in terms of inverse powers of R. So this, you can think of this as an expansion of phi near R = infinity. And here I've written down the two first terms in this expansion. And we can explicitly compute what is the exponent of R in those two terms. And this can be explicitly expressed in terms of the Klein-Gordon mass. And you already see here that somehow alpha equals to -9/8 is a critical parameter. This is the Breiten-Lorenz-Friedman bound. And we're going to consider only the case when alpha is bigger than -9/8. Below that case, we cannot prove well-posedness of the initial boundary value problem using energy methods. So first of all, when alpha is exactly equal to -1, this is known as the conformally, let's say, coupled case, then we see that these exponents here are integers. This is r to the -1, this is r to the -2. And this expansion here is really the Taylor expansion of r times phi at r = infinity. And this is why I called this term here the Dirichlet data of the solution, because this is exactly the radiation field if you want conformal infinity. And this part here, the Neumann data, because this really corresponds in that case to the normal derivative, let's say, of the solution at the boundary in this conformally compacted field picture. Now, when alpha is not equal to -1, those powers here will not differ by an integer. Therefore, this is not a regular expansion at infinity. Nevertheless, we will still call this part of the expansion the Dirichlet data and that part here the Neumann data. And when we want to prescribe, let's say, 0 Dirichlet data at infinity, we're just going to assume that this part of the expansion here is decaying sufficiently fast near infinity. And similarly for Neumann data. Okay, so now we can ask the question, how do we prove well-posedness for the linear Klein-Gordon equation on an asymptotically ADS spacetime by prescribing, let's say, 0 homogeneous Dirichlet conditions? Well, this is a very non-trivial question. It was first answered by Vassi, who proved well-posedness in the case when alpha is bigger than -9/8. Now, if we switch our attention to the nonlinear case, to the case of the nonlinear Einstein-scalar field system, and ask ourselves how do we prove well-posedness, then the case when alpha is equal to -1, the conformally regular case, in the case of Dirichlet conditions, when we want to prescribe this part to be 0 at infinity, this follows by modifying the work of Helmut Friedrich. But if we want to either consider Neumann boundary conditions or look at more general values of the Klein-Gordon mass, look at the conformally singular case, then this suddenly becomes a very difficult problem. And definite results are only known within spherical symmetry. So for the spherically symmetric Einstein-scalar field system, Holzinger and Spulevisi proved well-posedness when homogeneous Dirichlet boundary conditions are imposed when alpha is bigger than -9/8. And when alpha is in addition smaller than -5/8, then we also have the freedom to prescribe this term here. Right? Because when alpha is very large, this term here is already very fast decaying, and therefore we cannot use L2 methods to prescribe this as a well-posed Neumann data. So nevertheless, Holzinger and Warnick proved, let's say, well-posedness for, again, the spherically symmetric Einstein-scalar field system for a very general class of boundary conditions, which includes Neumann conditions when the Klein-Gordon mass lies in this range. Okay, so for the rest of this talk, we're going to look to the case when alpha is exactly equal to -1. So when we're at the conformally regular case. And we're going to be interested to both case of, let's say, we're going to study both homogeneous Dirichlet boundary conditions and homogeneous Neumann boundary conditions. These will be the two choices of reflecting boundary conditions that we're going to adopt. Okay, so in this context, in the context of the conformally coupled scalar field with, let's say, Dirichlet boundary conditions, what is known so far about the ADS instability conjecture? Well, the first result in that direction was by Bizon and Rostvorovsky back in 2011, who let's say, studied the problem both numerically and heuristically. And numerically, they evolved small initial data under Dirichlet conditions for a long time, and they realized that those data eventually reach very close to the regime of black hole formation. This observation, if you want, verified the validity of the conjecture numerically. But more than that, they also suggested a heuristic mechanism for why the instability should happen. And so what was the proposed instability mechanism? Well, the mechanism was a mechanism of resonant mode mixing. So what did they do? So this works as follows. So suppose now that we look at the equation for the scalar field, because remember, this is the equation that captures most of the dynamics of the system here. And looking at this equation in proper coordinates, this takes the following semi-linear form. On the left-hand side here, we have the Klein-Gordon operator on ADS background. And alpha here, remember, is exactly equal to -1. And on the right-hand side, we have a nonlinear term, which involves the Hawking mass, everything here. So this term, you should really think of it as a cubic term in phi, which, however, is non-local. And also it contains these inverse powers of r here, which blow up near r equals 0. But nevertheless, it's a cubic term in phi. And what we can do is that we can study this equation perturbatively. This is, as long as we're still close to the ADS background that we're perturbing, it makes sense to look at perturbative solutions of this equation. So we start by first looking at solutions of the linear Klein-Gordon equation. And for the linear Klein-Gordon equation, exactly because of the symmetries of the ADS background, we know that any solution decomposes into a sum of modes that evolve independently from each other periodically. So any solution of the scalar field equation can be written as a sum of modes which do not depend on t here. Then what we can do is that we can plug in this expression to the right-hand side and look at the first-order perturbative correction by solving this forced equation. Right? So the first-order correction will solve box of the correction equals to the right-hand side produced by the linear part. And if we do that, then we see that our perturbative solution actually can be decomposed into a sum of modes which are slowly, of course, these factors here are not time independent, they depend on time, but they only oscillate slowly in time. And through these nonlinear interactions, those can potentially exchange energy with each other. Now, in this setting, what Bizon and Rostvorovsky noticed is that when Dirichlet conditions are imposed at infinity, then there are resonant interactions in this system of modes. Namely, there exists a sequence. Actually, in that case, the spectrum of the linear wave equation is exactly the integer numbers. And therefore, there exist tetrads of frequencies which satisfy this relation. Actually, there's an infinite sequence of those numbers which satisfy this relation. And when this is the case, then we see that what happens is that the kth mode, if we look at the equation for the kth mode, the contribution of the L, M, and N mode into the right-hand side produces a non-oscillating factor. And therefore, this has the effect of slowly driving energy from lower frequency modes into higher frequency modes. So this was the perturbative picture discovered by Bizon and Rostvorovsky, and they suggested that this resonant mode mixing mechanism is what drives the system to eventually collapse into a black hole. So since that work, there was a huge explosion of numerical and heuristic works studying not only this problem, namely not only the problem of the existence of small perturbations of ADS collapsing into black holes, but more generally the problem of how many perturbations actually have this problem. You know, in the space of initial data around ADS, how large is the space of data which collapse into a black hole? And you know, is this a generic set, or are there generic sets of initial data which do not collapse into black holes? I'll come back to this in a second. So here I'm just listing a few of those names. But let me stress here the following, that all those works here, and the work of Bizona-Rostorowski that I described before, they heuristically, they're based on this perturbative approach. And of course, a perturbative approach can only make sense, can only be turned into a rigorous approach in the first stage of the instability, when the spacetime is still close to ADS and therefore can be seen as a small perturbation of that. However, if one wants to prove, indeed prove the ADS instability, indeed go all the way up to the regime of trapped surface formation, then one has to do something else. One has to move away from the perturbative regime. And this is what I'm going to tell you in a few slides. But for a moment, let's stay here and let's discuss a little bit some related problems. So as I said, the ADS instability conjecture is, if you want, the simplest possible case of turbulence appearing for the Einstein field equation, because this conjecture only claims the existence of an unstable family of initial data, right? But the next question to ask is what happens to generic perturbation? So in particular, if I look here at the space of initial data around ADS, we know, so the ADS instability conjecture claims that there exists a curve of initial data which approach the trivial ones, which collapse into black holes. Now the question is, how many of those initial data actually collapse into black hole? And in particular, can one find sets of initial data of positive measure with the property that they do not collapse into a black hole? They give rise, for example, to quasi-periodic solutions. Well, this is a highly debated question in the numerics literature. The answer is not clear, I have to say, but the most relevant rigorous result so far is by Sakis Hadjikaleas and Jacques Moulevessi, who showed that for a toy model of the Einstein-scalar field system, in fact, for a semi-linear, for a few actually semi-linear equations on ADS background, there exist quasi-periodic perturbations of the trivial initial data, which can be arbitrarily small initially. Right? So that's if you want, that's the result, if you want, is somehow the analog of that result in the case of the Einstein equation would be that there exist special quasi-periodic solutions which can be arbitrarily small initially. But now the question whether these actually occupy a set of positive measures in the space of initial data, that's a different question that I'm going to discuss later. Now, there's another question that one can ask, which is the following. Okay, so the ADS instability conjecture claims that at some point a black hole is formed. Then one can ask the question, what happens to that black hole solution? So how does the black hole exterior look like once it's formed? So does the exterior asymptotically settle down to something stationary, or do crazier things happen? Now, this is a question which is non-trivial only outside spherical symmetry. Within spherical symmetry, it is expected that actually once a black hole is formed, once Schwarzschild ADS, let me finish. So once a black hole is formed, one expects that it settles down to Schwarzschild ADS exponentially fast. And this, there is, for example, the result of Holzigel and Moulevessi saying that small perturbations of Schwarzschild ADS in spherical symmetry for the Einstein-scalar field system converge exponentially fast to that to Schwarzschild ADS is related to that. However, outside spherical symmetry, it's not clear what happens. And again, on Schwarzschild ADS, if one looks at the toy model of the linear wave equation, Holzigel and Moulevessi have shown that in general, linear waves on Schwarzschild ADS exterior decay only at a logarithmic rate. In fact, there exist quasi-normal modes which live exponentially long with respect to their frequencies. And therefore, this means that there is enough time for those quasi-normal modes to interact non-linearly with each other once one looks at a nonlinear equation and produce, similar turbulent phenomena, right? Of course, related to that is the work of Diaz, Horowitz, Marolf, and Santos, who looked at the following question. So suppose that you want to prove that some quasi-normal modes interact with each other and exchange energy at the time scale in which they live in order to produce a non-trivial effect at smaller frequencies, then the best candidates of modes to look at are the modes which lie as close to the boundary of ADS as possible. These are the quasi-normal modes with the lowest overtone. These are indeed the quasi-normal modes which are supported as close to the boundary of ADS as possible. And one can ask the question, okay, what happens to the spectrum associated with those modes? In particular, can one find a system, like a system of modes interacting resonantly with each other? And the answer to that is no. So if one just looks at those modes, then one can see that actually Diaz, Horowitz, Markov, and Santos computed the difference of the real parts of those quasi-normal frequencies with the corresponding frequencies on ADS. And they found out that the contribution of the Schwarzschild mass to this difference is actually bounded from below by some polynomial factor. Oh, here's a mistake. This should have been omega j to the -1/2 here. I'm sorry. And this means that those modes cannot interact resonantly in the perturbative timescale. Of course, this does not settle the question. Based on this observation, that paper actually conjectured that Schwarzschild ADS could be stable for large timescales. But in fact, there is more room for instability there. One can look at different modes which are not the lowest lying ones, or interesting phenomena could happen at a timescale which is slightly longer than the perturbative timescale. But a good toy model, a good toy question to study, which would help understand what happens to actually the perturbations of Schwarzschild ADS, is the question of, is understanding the properties of the conformal defocusing cubic wave equation of Schwarzschild ADS. And in particular, understand whether this equation exhibits weak turbulence or not. This is a very clean equation to study. It has a preserved positive definite energy. And somehow the question of whether, let's say, this transfer of energy from low frequency to high frequency occurs should help understand the behavior of the Einstein equations. Anyway, let's go back to the problem of the instability of ADS for the Einstein-scalar field system. And what I want to do now is that I want to sketch to you a proof of the conjecture in the case of the spherically symmetric Einstein-scalar field system. So first, I'm going to give you a heuristic mechanism, and then I'm going to tell you how this mechanism can be rigorously implemented to give a full proof of the conjecture. Okay, so as I said before, there is no hope of using the perturbative approach to give a full proof of the conjecture, because at some point, if one wants to prove that a black hole is formed, one has to leave the perturbative regime of ADS. So instead, the way we're going to prove the conjecture in that setting is by studying the interaction of short pulses of matter in physical space. And since the advantage that we're going to have by working in physical space is that we're going to be able to use the monotonistic properties that the Einstein equations have when expressed in physical space. Okay, so let me describe heuristically a little bit what we're going to do. So again, we want to prove the ADS instability conjecture. So we want to construct arbitrarily small perturbations of the trivial data, which eventually create a trapped surface. So how are those perturbations going to look like? So here I'm just looking at the Pendulus diagram of the solution. So I forget about the spherical directions. Here is only the time and the radial direction written down. And at t equals 0, at time t equals 0, I will construct the initial data to be like a large number of short bumps of scalar field. So these initial data are going to give rise to a large number of short pulses, which initially I'm going to assume that they move towards the center, r equals 0. Now, these beams are going to be very narrow. And this will mean that away from the center, away from r equals 0, since they're going to essentially, the equation will actually reduce by the geometric optics approximation to the Einstein-null dust system. So away from r equals 0, the Einstein-scalar field system for such short pulses reduces to the Einstein-null dust system. Near r equals 0, of course, one has to do something else because the geometric optics approximation breaks down, but we're going to look at that a bit later. So for a moment, let's assume that we have a large number of initial pulses that initially move towards the center. Then, once they reach close to the center, they rearrange themselves and start moving outwards towards infinity. Then each of those pulses is going to be reflected at infinity. Remember, we have imposed reflecting conditions at infinity. And through this process, those pulses are going to overlap with each other and therefore interact nonlinearly. Okay, and what we want to do is that we want to keep track of those interactions for a long time. Okay, so first of all, let's see how we're going to measure the energy content of each of those pulses. So ideally, if we assume that, again, this is heuristic what I'm telling you now. So if we assume that here we have an ingoing beam of matter, if we assume that most of the matter is contained inside that beam, then the renormalized Hawking mass in the exterior region here and here, it's constant here and constant there. So we can, so what we're going to do is that we're going to measure the energy content of the beam simply as the difference of the renormalized Hawking mass in those two regions, and that energy content is going to be constant along this beam as long as this beam does not intersect another beam, right? And at some point, we want to show that a trapped surface is formed. So at some point, we need to show that there exists a sphere of symmetry in the spacetime for which 2m over r, m is the Hawking mass, r is the radius of the sphere of symmetry, becomes bigger than 1. Okay, so in order to do that, this means that we have to look at the evolution of the Hawking mass. And in particular, this means that we have to look at the evolution of the energy contents of those beams as they interact with each other. So let's focus at two beams interacting. So here we have one beam, zeta bar, which is ingoing, it goes towards r equals 0, and then other beam which is outgoing, moves towards r equals infinity. And I'm just expressing here everything in double null coordinates. So u and v coordinates here are just double null coordinates. So if we set up this, if we set up those beams correctly initially, then we can make sure that those interactions take place away from r equals 0, where the geometric optics approximation holds. So if the geometric optics approximation holds, then there's actually a very, so in the Einstein-scalar system, which is the geometric optics approximation for the Einstein-scalar field system, the equation for the Hawking mass actually simplifies a lot. And we actually get this equation here for the Hawking mass, where the right-hand side here actually is positive outside a black hole. So this term here is, with a minus sign in front, is always positive. This term is always non-negative. The other term is non-negative as well. Therefore, if we want to look at the evolution of the energy content of this beam, the ingoing one, so remember the energy content is simply, let's say, the difference of the Hawking mass here and here. Infinitesimally, this is just the dv derivative of the Hawking mass. And now we just want to study how the dv derivative of the Hawking mass changes as we move in the u direction. So we just have to integrate this equation along this region of interaction. And if we do that, and we consider the limit when those pulses are very narrow, then we get the following approximate formulas for exchange of energy. In particular, what we see is that the energy of the ingoing beam increases. It increases by a factor which depends on the energy of the other beam, and it's also stronger when the interaction takes place close to r equals 0, when the beams are more concentrated. And similarly, the energy of the outgoing beam necessarily decreases by a similar factor. Okay, so this is what we have to keep in mind, that whenever two spherically symmetric beams interact, the ingoing beam always increases its energy while the outgoing loses energy. Okay, so let's now focus on two beams of initial data, starting from t equals 0. How do they evolve in time? So if we have two beams here initially which are ingoing, then they're first going to interact in this region and 0 here. And this region, if the initial separation of those beams was relatively small, is going to be relatively close to r equals 0. Therefore, the interaction here is going to be stronger because remember, there is this 1 over r factor here. And in this region of interaction, the beam which was initially to the right gains energy. Then the opposite thing happens close to r equals infinity. The beams will interact again here. Now the same beam here is going to be outgoing, and therefore it's going to lose energy. But because, again, if the separation of those beams was not very large, then this interaction here is going to take place close to r equals infinity. And therefore, the interaction here close to infinity is going to be weaker than the interaction close to r equals 0. So therefore, all in all, we see that after these two interactions, the beam which was initially to the right strictly gained energy from the other beam to the left. Right? Therefore, this means that if we have a large number of beams initially, and if those beams retain their shape as time evolves, then through these nonlinear interactions, energy will keep flowing from beams which were initially to the left to beams which were initially to the right. And if we had made sure that beams which were initially to the right were actually narrower, then we would actually have a flow of energy from larger scales to smaller scales. Okay, so this is the instability mechanism that we want to make use of in order to prove the ADS instability conjecture. And my claim is that actually these heuristics that I told you about so far can actually be turned into a rigorous proof of the ADS instability conjecture. In fact, I have already utilized such a mechanism in the case of the Einstein-Maslow-Vlasov system back in 2018. The advantage of that's also a system that I studied under spherical symmetry. The advantage of that system was that the Vlasov equation is just the equation telling you that the Vlasov matter now lives on the tangent space of the spacetime, and the Vlasov equation simply tells you that the massless Vlasov equation tells you that Vlasov matter is propagated along null geodesics. Therefore, such a matter model allows for matter beams which are perfectly localized. In particular, the regions between those beams are exactly vacuum, and this simplifies a lot the combinatorics of the problem. However, I claim that a similar mechanism can also be applied into the case of the Einstein-scalar field system. And the theorem I have is the following. The theorem is actually what you would expect for the ADS instability conjecture. The theorem is that this conjecture is true in the case of the conformally coupled Einstein-scalar field system. That is when the Klein-Gordon mass is exactly equal to -1, with either Dirichlet or Neumann boundary conditions infinite. In particular, claim that there exist initial data which are arbitrarily small with respect to the BV norm of Christodoulou, more than that in a minute, such that if we look at the evolution of those data with either Dirichlet or Neumann boundary conditions, then eventually they collapse into black holes. And the BV norm that I wrote down here, this is simply, so here I've set up the initial data in terms of characteristic initial data. So I prescribe initial data on the cone U equals 0 initially. And the BV norm of Christodoulou, you can think of it as a BV norm of the derivative of the scalar field initially. So this is a scale invariant norm. Scale invariant, of course, if you also rescale the cosmological constant appropriately. And as you can see, it's a low regularity norm. So now you might ask, okay, so why do I study this problem in such a low regularity setting? How do I know that these instabilities that I'm seeing are not just an artifact of the low regularity of the initial data norm? That secretly initial data which are small in this norm are actually large with respect to the better norm. And my answer to that is that, first of all, that's a good enough norm to look at in order to study this problem. And this is because, first of all, the initial boundary value problem with respect to that norm in the conformally coupled case is well posed. In particular, this means that the trivial solution is Cauchy stable. And this follows by just modifying the work of Christodoulou, who proved the well-posedness of the Einstein scalar field system in spherical symmetry in the BV set, in the BV class, in the asymptotically flat case. The modifications are actually very simple in the case when we're looking at the conformally coupled value for the Klein-Gordon mass. I actually don't know how to do that in the singular case. And moreover, in the absence of confinement, so in the case of lambda equals 0, it follows by the work of Christodoulou that Minkowski spacetime is actually stable under spherically symmetric perturbations, which are small with respect to the BV norm, and are also localized initially. Therefore, this means that the instabilities that we're seeing here, they are just, they are produced, if you want, by the presence of a confining boundary at infinity. So in the absence of confinement, that result of Christodoulou tells you that there is no instabilities appear. So it's like so those two remarks here are here just to justify. Actually, I'm trying to convince you that choosing the BV norm to measure the size of initial data is good enough to study this conjecture. Okay, so let me tell you a little more about the proof. And what I want to do in this, what I need to do is that I want to take the heuristic mechanism that I told you about before and actually turn it into a rigorous mechanism. And so what I'm going to do is that, again, I'm going to set up my initial data into a large number of matter beams. And those beams here, each beam here has to be very narrow. Each successive beam here is going to be narrower than the previous one. And there's going to be a hierarchy between the widths of each beam with respect to the previous one. And moreover, the distances between those beams have to be very small, but still large compared to the widths of the beams. More of that in a few seconds. And if we believe the heuristics that I sketched earlier, we expect energy to keep flowing from the larger beams initially towards the narrower beams to the future. Okay, of course, now you might complain that this heuristic mechanism that I described before, it's only valid as long as the scalar field remains organized into a large number of beams which are almost perfectly localized. But of course, beams have the tendency to decohere. And decoherence is our biggest enemy here, because so initially we have the initial data arranged into a large number of beams. Once the beams decohere, then the solution will stop looking like a large number of beams. So all those heuristics that I told you about before are just useless. And unfortunately for us, we cannot get away with decoherence. So there is no way to set up the initial data so that decoherence is really negligible. And this is because of the scaling invariant way that we measure the smallness of the initial data initially. So what I claim is that every beam, once it reaches close to r equals 0, will lose a certain amount of energy to decoherence. So a certain amount of energy will just move away from the beam in the space. And why is this the case? Well, if we look at in double null gauge, if we look at the conformally coupled scalar wave equation, then this equation takes the following form. So du dv of r phi, this is the term that was also there in the flat case, plus a nonlinear term which contains a term like m over r squared times phi is equal to 0. And now this term here, the fact that we have the presence of this term m over r here is what creates decoherence close to r equals 0. And in fact, decoherence is stronger when m over r is bigger. And remember, at some point, we want to be able to show that m over r becomes larger than 1. So we want to show that at some point the trapped surface is formed. So there's no way to get around that. At some point, we have to deal with a regime where decoherence is substantial. Okay, so how do we do that? Why can't we get away with that? So why doesn't this destroy the whole picture? Well, what saves the day at the end of the day is the fact that we have two scale invariant quantities that we take into account. One is the BV norm. This is the norm that we measure the size of the initial data. And the other is the quantity m over r. This is the quantity that controls decoherence and also some other things about the geometry of the spacetime, trapped surface, and so on. And again, what saves the day at the end of the day is that those two quantities are not comparable. The BV norm is a stronger scale invariant quantity than m over r. And in particular, what can happen is that we can, and what we actually show that what we make sure happens is that for most of the time along the evolution, the BV norm of the solution grows larger and larger while m over r remains smaller and smaller. And that at some point, the BV norm becomes very large, and then within a time interval of size 1, the quantity m over r jumps from being very small to being of size 1. Okay, why can this happen? Let's look at the scalar field, and let's decompose the scalar field into a sum of model scalar fields which satisfy a better equation plus an error term. So those fields phi I here, these correspond to the beams of matter, and this, if you want, this equation here is the equation that would be satisfied by those fields in the absence of if we ignore the nonlinearity, right? So here we decompose phi into a number of model solutions, if you want, of an equation which creates beams that are very well localized. And then this error term here, this captures the effect of decoherence. Okay, so the crucial thing to do here is to look at the equation satisfied by the error term and try to show that this error term here remains small for very long times. So if we look at the equation for the error term, this looks as follows here. So here we have, on the left-hand side, we have an equation that morally looks like the equation that we had before. And then on the right-hand side here, we have a forcing term that comes from those beams phi I here, plus multiplied by some potential. This is the same potential that appeared before in this slide. And the crucial thing here is that this potential here contains m over r. And moreover, for those beams phi I here, we know a lot of things about their support and the size and so on along the evolution. And the claim now that, okay, I'm not going to actually write down how the estimates are produced, is that for a long amount of time, if we choose the initial hierarchy of the widths of the beams and their separation appropriately, then we can make sure that the BV norms of each beam is relatively small. The BV norm of the total solution grows larger and larger, but the BV norm of the error term here also remains small. This is the statement of this. Okay, so this goes on for a long time, but at some point we want to be able to show that m over r becomes larger than 1. Right? So at some point we have to go away from the previous regime. So you can think of this regime here as being semi-perturbative. Somehow, some parts of the solution remain small, and we can deal with them perturbative. Some others are going larger. And then in the last step, what we do is the following. So by almost fine-tuning the initial data, we want to make sure that there exists a time at which the scalar field attains the following configuration: that the beams now are arranged in a way that so that the scale invariant size of the first beam is small, is of size delta. The scale invariant size of the second beam is of size delta times a factor smaller than 1, e to the minus delta. The next one is, again, multiplied by this smaller factor, the next one, so on. So this means that the total BV size of the solution here, so if you sum over all those terms, this is bounded from below by some constant, but not necessarily very large, like 10 or something. So once we reach this configuration, then if we let those beams evolve for one last time, and if we're very careful to keep track of the coherence of all those points, then what we see is that after all those interactions, those beams emerge having all of them the same scale invariant size. So in particular, the BV norm now of each of those beams is of size approximately delta. Now, the number of beams was very large. In particular, if you want, the number of beams emerging from here is much larger than, let's say, 1 over delta. Therefore, this means that if we focus here on the last beam that is ingoing here, the last beam now will cross all those outgoing beams, and that if you want so this beam will feel as if it intersects a non-trivial amount of energy at each scale here for a very large number of scales. In particular, you see the total BV norm along this direction here now is very, very large. And what happens is that in that case, this beam, if you want, you can think of this beam as if going through a discretely self-similar background. And therefore, the amount of blue shift that it undergoes is very large. So it can be made as large as we want if we choose the initial number of beams very large. Therefore, even though this beam initially had very, very small energy compared to its width, after all those interactions, the ratio of the energy contained in that beam divided by its width can be very, very large. And once this is the case, then we know by using a trapped surface criterion, formation criterion of Christodoulou in spherical symmetry, we know that this beam will collapse into a black hole before it has the chance of reaching very close to R equals 0. Okay, so once we're here, we know that a black hole will form, in this small amount of, in this small space-time region here. More or less, if you want, that's it. These are the main parts of the proof. And let me make a few more comments before I finish regarding generalization. So first of all, okay, that's what I described to you is a proof of the ADS instability conjecture for the Einstein-scalar field system. But as we said before, there are other interesting questions. For example, what happens to generic perturbations of ADS? Do they collapse to black holes or not? So first of all, we expect that not all perturbations will collapse. There will probably exist some quasi-periodic, some choice of initial data which give rise to quasi-periodic solutions. And the results of Sakis Hadjikales and Sakis Moschidis point to that direction. However, if one asks me, whether, oh, sorry, Martin, am I out of time?
No, you're good. You're good. I'm just checking
okay.
for questions. You're fine.
Okay. So the question of whether the set of initial data that give rise to non-collapsing solutions, whether this is of positive measure or not, that's a trickier question. And given that this instability mechanism that I described to you right now is quite robust, and it also takes effect in some sense beyond the perturbative timescale, I can probably discuss about this in the question, I would expect that actually quasi-periodic solutions are very special, and that probably generically one has the situation that we saw before. Nevertheless, the most interesting question, if you want, in that case, is the question of proving the ADS instability conjecture in vacuum, in the absence of matter. And of course, in that case, one cannot reduce the problem under spherical symmetry. One really has to work with 3+1 dimensions. And of course, the mechanism that I just told you about is very spherically symmetric, generalized. However, I would expect that in principle, the main ideas could be generalized. Everyone could expect, let's say, a large number of pulses, which are very regular in the angular directions and very short in the radial directions, of interacting with each other and exchanging energy in a similar pattern. However, in order to implement such a mechanism there, one has to actually first solve a few very fundamental, very difficult questions. So question number one, which if this is not answered, then anything else doesn't make any sense, is whether one can actually prove well-posedness for the initial boundary value problem in a class of initial data which allows for such almost spherically symmetric bumps. In particular, whether one can prove well-posedness for a class of initial data which lies at the level of H3 halves, but with additional regularity in the angular direction. More than that, one also has taken to somehow deal with the effects of the boundary. Now, in spherical symmetry, in the conformally coupled case that we were talking about, the effects of the boundary conditions were actually trivial. Actually, one could explicitly keep track of how the solution looks like near the boundary. But in vacuum, it's not clear what are the gauge conditions, for example, that one can use in order to not see problems from the boundary accumulating over large timescales. For example, if one tries to work things out in the gauge used by Helmut Friedrich, which is involves somehow conformal transporting quantities along conformal geodesics, then one would see caustics, for example, appearing in not very large timescale. So that's a very non-trivial technical issue that also has to be there. So that's, of course, a very open problem, which I think is very interesting. And I'd like to end my talk here, and thank you all for your attention.
All right, let's thank Georgios for a beautiful talk. All right, so are there any questions? Oh, yes, there's a Q&A question.
I see something. Oh, much. Sorry, I'm just reading it. Okay, so let me, first of all, for question number 2, so why do beams on my plots do not reach the origin? That's just a matter of how I draw everything. Of course, the support of the beams will go through the origin. I just drew things like that. Now, but the first question is actually very interesting. So indeed, I do not use the resonant condition in this argument explicitly. And I would expect that the same mechanism goes through in the absence, you don't need the spectrum to be resonant for the mechanism to go through. That being said, probably in all of those cases, of course, the spectrum is asymptotically resonant in some sense. But nevertheless, what I want to say is that this mechanism that I described right now, it probably kicks in at a timescale which is larger than the perturbative timescale. So if one has a resonant spectrum, somehow one would expect that the following statement is true, that you start from some initial profile, you multiply them by epsilon, and then you expect the instability to appear at time, let's say, epsilon to the -2. Now, the initial data that they look at, they don't have this form. They're not of the form, initial profile times epsilon, because the smaller the size of the initial data, the larger the number of the beams, and they're supporting more and more, let's say, modes initially. However, I would expect that, let's say, I don't know how to say that in a very good way. Yeah, nevertheless, okay, let's say it like that. But I would expect that what I described, it takes effect in a time scale which is larger than the perturbative. Therefore, it makes sense that it can also be applied to the case of when you have non-resonant spectrum. And those two. Yeah, sorry, is there something else?
No, I think.
Okay.
There might be. Is there? Yes, or there's a thank you from Macias. Yeah.
And also that's why, okay, let me also say something related to that. So when I talked about whether islands of stability of positive measure exist or not, this is why I said that I'm not sure whether, of course, I do believe that quasi-periodic solutions exist, but whether there exist initial data of, let's say, which are open sets around those quasi-periodic solutions, which live for a very long time, I don't think that statement is true, let's say, beyond the perturbative timescale, just because the mechanism that I described does not need, the spectrum to be resonant to taking effect. However, in the perturbative time scale, which is what people mostly see, for example, when they do numerics, probably the absence of resonances might tell you something about having solutions which do not collapse, let's say, in that time scale. Or something of this sort.
Okay, if not, well, let's thank Georgios for beautiful talk.
Well, thank you, Martin. And of course, we have to thank the organizer for this wonderful conference. Thank you very much.
Oh, thank you for joining us. Okay, well, all the talks will be on YouTube, so you can all follow them and you can all watch them if there's any ones you've missed. But thank you, everybody, for joining, and we hope to see you soon.